Lesson 36, solving equations graphically and word problems. Okay, so the solving these equations graphically should be review, right? So when we're solving these things graphically, I'm hoping you guys are at the point now where we know that the answer is going to be where they cross, right? So we have it laid out here for two steps, steps for two equations. A situation like this where you had like one side equal to another side, or for one equation. So that would be like this, right? So that'd be if it was equal to 0 on the same on one side. But I'll show you when we get going that this really is the same thing in the end. But to do that, let's solve this one graphically. So A, and I'll use a TI calculator for this one. So let's see what we get. So I'm just going to type in, well, the way we do this is we type y1, oh, not all the way, for one side. So that'd be like my y1. And the 3 would be like my y2, right? So the 3, that's just a straight line at 3. So let's graph both those things and see what we get. So if we graph our y1 as 4, and then sine, and then we can't really type theta in the calculator, so I'm going to type in x, right? So that's our variable, so x, and then close the bracket, and then minus 5. All right, and then for y2, I'm just going to graph the line 3, so the horizontal line at 3. So let's see what we get. So that blue one happening there, that is going to be our sine wave, right? That's going to be this, okay? Which actually kind of makes sense, doesn't it? This thing would have a vertical stretch of 4, and it would have a midline at -5, and that's what's happening, right? That midline is down at -5. And then look at where the line 3 is. That's actually above it. So in this case, there would actually be no solution here, wouldn't there? Right? It actually doesn't cross at all. So I'm just going to write no solution, or does not exist. So D and E, because they just don't cross, right? So for the sake of time, I'm not going to sketch that one out either. If you want, it's down there and the line's up there. But yeah, I'm just going to leave it there and say that one actually doesn't cross, right? So that's how you do it on a TI calculator, right? So a lot of this will be review for you guys. I'm going to play around with this one now too, and I'm going to use the Desmos calculator just because it's a bit nicer to look at too when I'm showing you. But so that one, what I'm going to do here now is I'm just going to graph this side, right? This will be my y1, and I'm not even going to graph a y2. But technically you could, right? If we did the same thing, if I graph this as my y2, well, that would be the line y is equal to 0, right? Which is just our x-axis, isn't it? So in this case, if I just graph y1, well, what I'm looking for is just where it crosses the x-axis. Okay, so that's really what it says here, where are the zeros, so where is it across the x-axis? But in the end, it really is where it's crossing those 2 points as well, right? So it's really the same thing. Okay, so let's look at this. So if we've got tan squared x minus 3 tan x, right? So I'll just turn this on now. So we'll see, whoop, I'm up a little too far here. Okay, I'm just going to go down a bit. Okay, zoom in like that. All right, so we said that the solutions here are where it crosses the x-axis, or if you really like, I could type in y is equal to 0, right? So it'd be crossing that same point, isn't it? But that is the x-axis. So now this one's nice because I can actually just click on the graph and it tells me where those points are, right? So it knows interesting points. So I'm going to show a few of those, okay, and maybe even go back this way a bit. And we'll start to kind of see the pattern here, right?
Hey, Mr. Brown.
All right, so yeah, now the problem is we need to be able to give this answer in a general form, right? Because you can see if we zoom out here, this thing actually goes on and on and on forever, doesn't it? There's actually like an infinite number of solutions to this problem. So we need a general solution for this thing. So, whoop, sorry, probably making you dizzy. Okay, so let's look at this and see if we can make sense of it. So this would be, oh shoot, I want to see all of them. There. Okay, so if you can make a quick sketch of this on your graph, just pause it, and just roughly, right? Just kind of make a sketch of what's happening here. I think that'll kind of help to remind you what's going on. But what I'm going to do from here is I'm just going to write right on the screen here. And I'm going to look at, 0, right? So what's happening here? So from the point 0, Well, can you see that like one of the patterns here is we start here, and then we go to pi, and then I didn't write it again, but then this point here would be 2 pi, right? That's how far that one's going in my x direction. So that's going to be 2 pi. So our first general equation here, I could say, is that theta is equal to, and then really what I can do is go, well, you could go 0 plus pi n, right? Like start at 0 and then add pi and then times n, where n is a member of the integers. But that's a little awkward, isn't it? So I'm just not going to like write that 0. So in the end here, our answer would just be theta is equal to pi times n, where n is a member of the integers, right? So what that accounts for would be if n was 0, that gets me to 0. If n was 1, that gets me to pi. If n was 2, that gets me to 2 pi, and then the pattern goes that way, right? But it also does the negative values as well, right? So if n was equal to -1, then my answer would be negative pi. Okay, so then that'll work for that one. So now we handled those ones, but you can see we've got like a different pattern happening here, right? From like this point to this point, right? And the distances between these will also be the same, right? They're going to happen at constant intervals as well. So how are we going to figure out that one? Well, what we should do here is just go, well, this number, 4.391 minus 1.249. Right, so that would be, so you'd write it out and go, all right, down here, 4.391 minus 1.249, and we end up getting 3.893. Okay, so that's the distance between these points, and actually that would be the distance. So 3.893 is the distance from there to there, and it's also going to be the distance from here to here, right? If you go 3.893 would be the distance between those points. Okay, and you can try it out, right? If you go this minus this number, you end up getting that number. Okay, so now good, we can actually make our pattern here now, right? So then theta 2, or I'll call that first one theta 1, this would be theta 2 would be, well, we'll start here, 1.249, and then plus, what was it, 3 point, sorry, I lost my pen there, 3.893, and then here's where we're going to introduce the n again. So this will be times n, where n is a member of the integers. So we got the same thing happening, right? Where really we're starting at this point. We're starting, here, clean this up a little bit. We're starting here, and we're either adding 3.893 or we're subtracting 3.893. And then in multiples though too, right? So it'd be 2 times that would get you to the next point, like way over there, off the screen. And then way over there if we went -2, okay? So that's the idea there. So there's our 2 solutions for that one. Okay, so now take a second to write that down. I just want to show you one more thing before I leave this, just with this graphing. So yeah, those are your answers. Pause if you got to. I'm just going to clear this. So if I clear it, I want to show you that this would have been actually the same answer if we would have done it a little bit different. So if we would have rearranged this, so on our sheet here, right, it was tan squared theta minus 3 tan theta is equal to 0. But what if I brought the 3 tan theta over to the right side, right? So that'd be tan squared theta is equal to 3 tan theta. So I should be able to graph that, and it should give me the same values, right? I'll just show you how that looks, just so you know that it does all work out. So I'm going to type in, so clear that, tan squared x, and then I'm going to graph one more, which would be just 3 tan x. So at first glance here, it looks like something's wrong. We've got the one pattern here where it's going up by pi every time, right? That handled the first angle. But it looks like we're missing our second angle. But remember, the solutions are where they intersect, right? So if I zoom out a little bit, let's see. You can see I have a whole another set of answers up here, right? Here's my missing answers. Those are the ones from before, the 1.249, right? And then the 4.3, yada yada, right? So you can subtract those and get the same difference. So it works either way. It's probably simpler if you use the x-axis one, but it does. Sorry, the one thing I forgot to mention there, guys, I kind of looked at this a little bit funny. I forgot that it was this. What I gave you there was the general solution, so that would be for all solutions. But they gave us this restriction, didn't they? They said, so yeah, if you're looking at this, and we make our points again, just so we can all see them clearly. Yeah, it was saying that we had the restriction, right? We had that restriction of 0. So theta has to be greater than or equal to 0 and less than 4 pi, right? So I did it for all of the answers, right? But we have to just actually restrict our answers there. So let's do that again. This would be theta is equal to, and then the first one there would be pi times n, where, and now what I'm going to do is I'm going to restrict my values for n. I'm going to say where n is greater than or equal to 0 and just less than 4, and this, I think this will make sense in a second, where n is a member of the, now I'm not really going to say integers anymore because I've already restricted it to my positive numbers, so I'm going to say just whole numbers. Okay, so then let's check if that makes sense, right? So n has to be greater than or equal to 0, so that means I could put 0 in there, which makes sense, right? Because that would give me that 0. And then n has to be just less than 4, because again, this has to be less than, not equal to pi over 4, just less than 4. Okay, so that takes care of our first one. And now the second one there, if we were restricting it this way, so our theta 2 would be, let's look back at it. So we started at 1.249, right? I'll call that 1.25, around that. So that would be 1.25 plus pi times n, where n is greater than or equal to 0 and less than 4. And then when n is a member of the whole numbers. All right, so if we look closer at this one now too, right, that we could throw some numbers in. If I put 0 in for that, then that would just be back to our point of 1.25. So that'd be right there, right? If I put 1 in, then that's going to get me to 4.39. And then if I put 3 in, that's going to get me here. And then that's kind of it, right? Because if I go, here, I made it a little bit clearer there. So 1.25, that was that first one. And then if n was 1, that would give me to here. And then if n was 2, that gets me to here. If n was 3, that gets me to here. And now I can't be bigger than 4 pi, right? So I can't go over to this one. So n can't be 4, right? And that's really what we said here as well. We restricted it, so n is less than 4. So that would just be the numbers 0, 1, 2, and 3 is what this is restricting it to. Okay, hopefully that made sense. Okay, so now word problems. So with our word problems, what we're going to do is we're just going to be like applying this to a real world situation. So we're going to be given some data maybe, and we'll have to make an equation from it, or make an equation and then calculate something from that. So let's go down to our first example. So it says write a sinusoidal function that models the average temperature in Brandon, Manitoba as given in the table. All right, so we get a bunch of data like this, and we want to write a sinusoidal function. So a sinusoidal function is going to be in the form y is equal to a sine b and then x minus c and then plus d, right? So all we really have to do is we got to find a, b, c, and d, and then we're done. So let's get started. One thing I think that'll help here is to like make a little, just graph this thing, just as a sketch though. We don't need to be perfect. So here, let's try this. All right. So if this is our graph on our x side, right, these are going to be like our x values here. That's going to be our months going across the x-axis. Okay, so that's like our x or our months. And then it's going to be our temperature along our y-axis there, right? All right, so let's make some ticks here. So I'll make, there'll be our first tick for January. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we're going to be able to figure out like our A value and our D value and some other information here. But really what we want to do is we want to figure out some kind of reference. We want to figure out maybe where our maximum and where our minimum are. Those are usually good points to find. So in this case, our minimum value is going to be right there, right? At the point 1 comma negative 18.3. And our maximum value is going to be right there. So let's roughly sketch those out. So when the month is the 1st, so January, we're going to be down here at negative 18.3. Sorry, the point would be 1 comma negative 18.3. Okay, so that's that point there. And then the next point is going to be at, well, when x is 7. So 1, 2, 3, 4, 5, 6, 7. So that's going to be up here. So that point would be at 7 comma 18.9. Now that's kind of good to get us started, because now we can see that this thing, there's my bottom or my minimum, and then it would come up there, and there's my maximum, and then it would go back down again, and then this thing would repeat the pattern, right? So let's see if we can make some sense of this. So now that we have that sketched out, let's find A. So our A value is, and this isn't on your formula sheet, we have to remember this one, A is going to be your max minus your minimum divided by 2. And remember what that's finding. That's just finding like half of the height of your wave, right? You're just going your top value minus your bottom value and then cutting that in half to figure out your amplitude. So that makes sense, right? So that'll be A is equal to, and your max is 18.9 minus your minimum of negative 18.3 divided by 2. So your amplitude is, so that'll be 18.6. All right, so I'm going to put a box around that because we're going to need that in a second. So there, 1 down, 3 to go. So let's move on to our, well, tell you what, usually it's easier to find your A and your D kind of at the same time. They're similar, right? The equations almost look the same. So our D value is going to be our max minus the min divided by 2. Okay, so your D value is going to be it's going to be 18.9 minus, or sorry, got that wrong, not minus, plus your minimum. So plus, and then your minimum was negative 18.3 divided by 2. So your D value is 0.3, which really makes sense, right? When we did this, the 18.9 and the negative 18.3, when we were finding our D value, we're finding what this line is like going up and down around, right? Like if you cut this line right in half, what would it be going around? And 18.9 is a little bit, has more magnitude than negative 18.3, right? So I was expecting that this line would be a little above 0, and it was. Okay? And remember, what we're finding here when we do this max plus min divided by 2, that's really just the average between 18.9 and negative 18.3. And again, this formula is not on your formula sheet. Okay? So, all right, next one. So 2 down, 2 to go. So now, typically we find our C value last. Okay, so I'm going to find my B value now. So for that one, our B is very closely related to the period of the graph. So whenever you're thinking B, you should be thinking, okay, I got to find my period, and then it's a simple calculation from there. So B is going to be equal to, and it's 2 pi over the period. Now the question is, what would the period be for a calendar year? Well, 12, right? It's going to be 12 months. So this is going to be 2 pi divided by 12. So in the end, this would be the same thing as, so our B value would be just pi over 6. Now, you might be saying, yeah, but couldn't we have done this in degrees? Yes, you could. You could have done it in degrees as well. So it would have been 360 over 12 to get your B value. But then make sure if you do that, then your C value as well would be in degrees. Typically, we do these in radians whenever we're doing these real world problems like this. All right, so we got A, we got D, we got B. The last one to do is to figure out our C value. So now the C value, there is no great method for figuring out, exactly, for a formula or anything, right? With the C, what I need to do is I got to figure out how much has this thing been shifted this way or this way to give us our equation, right? So yeah, if we're looking at our graph here, then if we're thinking a sine graph, right? So if we're thinking sine, then sine typically, starts, so y is equal to sine theta, starts at the origin and then goes up and down like that, right? Our cosine graph, y is equal to cos theta, that thing starts here and then goes down and around, right? So we can actually choose, when it says sinusoidal function, we can either choose sine or cos. So we can make it either one. All that's going to change is how much we're shifting it. So now on this one, if we're looking at this, being okay, where did it, like sine would have started here and then shifted to here? And given the data that I have on the graph, I don't have a great method for figuring out how far that is from there to there, right? So instead of using a sine graph, I think I'm going to use a cosine graph because it's easier to look at the peaks here to see how far they've moved. Okay, so I'm going to focus on this one first. All right, so if we're looking at that one, here, I'm not even going to do it down here. I can just write it out. So we can write out our equation. So this would be y is equal to, and then I know what some of these numbers are now, right? So A, I'm just going to write down 18.6. And then instead of sine, I'm going to write cos. So it's going to be cos. And then my B value was pi over 6. And then my X value, oh, sorry, my X is just my X. And then my C is the one I'm looking for. So I'm going to leave that blank for a second. And we'll talk about what happens to it. And then plus D. And my D was 0.3. Okay, so I'm pretty much done there. But I just have to account for how much this thing has been shifted. So let's think about this. Our cosine graph would normally be starting up here at 1, right? Why don't I say this? Why don't I say that this was actually negative, right? It was flipped upside down, right over the axis like that. So if I put in a negative here and say this thing was flipped, okay, then from there, like it would have started right at that point, right? Because the negative cos graph would have been starting down here and then going up. So that would have been handling the negative would have got me to there. And then it looks like this thing has just been shifted to the right 1 unit. So a horizontal shift of 1 to the right would be minus 1. And there you go. There's our equation. Now I want to show you too that that's one of many interpretations of this, right? Because what about this? What if I would have said y is equal to, and then if I would have left my cosine graph positive, right? So instead of having a negative out front, flipping it down here, I left it positive. So that'd be 18.6 times cos, and then pi over 6. Those things don't change. And then x. And now in this case, what I'm going to assume is that this thing, my cos graph started here. It would normally start there. But it has been shifted 7 to the right to move the peak all the way over to there. So then what I would say is that it would be x minus 7. Those are exactly the same. Like if you graph that top one and graph the bottom one, you get the same number. Okay? And there's actually an infinite number of variations of this that you could do as well, right? Because this graph would continue on, this way, going around. And if you actually graph it, this is at the point, this is at 5, is where the next peak would be. So you could also say that this thing moved to the left 5. So it would also be true to do this. We could say y is equal to 18.6 times cos pi over 6. And then x. And now if it's moving to the left, this would be plus 7. or plus 5, sorry, I said it was. Plus 5. And then plus 0.3. So again, those are all the same graph, okay? Just notice that we had to flip that first one to make it work. But all right, next one. Okay, next one. So it says the London Eye has a diameter of 122 meters, and it is 135 meters from the ground to the top. It takes 30 minutes for one rotation of the wheel. Passengers board at the bottom of the ride, and the wheel moves slowly enough that it is not necessary to stop to let passengers on or off. We're at a sinusoidal function that represents the height of a passenger riding the London Eye. Over what domain is the function going to be valid? Okay, so to get our bearings here, let's actually write down well, a little diagram, I think. So let's do this. Okay, so I kind of cheated and used the tool to make the circle. Okay, so it says the diameter of this thing is 122 meters, right? So from the top to the bottom is 122 meters. And it says that from the very peak to the bottom here, right, from the ground is 135. So from there to there. All right, so now that we have that, roughly sketched out, right? That's not really the scale or anything, but let's write down our equation. So our equation is y is equal to a, and then sine or cos, we can decide after, but I'll just write sine for now. Sine, and then b, x minus c, oh, that was a bad bracket, and then plus d. Okay, so really if we're gonna make this equation, we just gotta find a, b, c, and d, right? So let's kind of focus on our well, a and d value first, because I don't think these would be so bad, right? So if you can imagine this thing spinning around in a circle, right? Okay, so I pulled this up for a second just so you can kind of see what's happening here again. So remember, so when this thing's going around the circle, right? You can see on my graph there what's kind of happening is they're going to start, probably like a sine wave. So they start at the bottom. And then as they go around, the graph would go up, they get to the peak and then down, and it's going to go around and around like that, right? As we're doing this. Okay. So if you think about it, the actual amplitude of this thing is going to be related to the actual circle itself. So if this is going around, so it's like up and down from here, if this was going back and forth, then the amplitude really would be the same as the radius of our circle. So A is actually pretty easy. Our A value is just going to be, well, half of the diameter is going to be the radius. So that's going to be 61 meters from there to there. So done. So we got A. So we can write it down if we like. So here, A is equal to 61. Done. All right, so now our D value. Can we make sense of our D value from this? Well, yeah, if the whole thing is 35, and I want to figure out, like what this thing is orbiting or going around, our D value is going to be like this line I just drew right there, right? So in that case, that would be 135. So D is going to be 135 minus 61. So our D value is going to be 74. Okay, so we found 2 already. So now we'll find our B value. So remember our B value is related to the period. So what's the period? I think they tell us, right? It takes 30 minutes for one rotation of the wheel. So that's going to be 2 pi over 30 minutes. Okay. So then that is really it. We kind of like to leave the pi if we can. So I'm just going to simplify that a bit. 2 over 30 would be the same as 1 over 15. So that would just be pi over 15. All right, so we got B. All right, so I think we have enough to kind of get going here. We'll have to figure out like our C and whether or not we flip it, but let's write it out. So we've got Y is equal to, and then, well, actually, to tell you the truth, let's kind of sketch it first. So this graph, if you think about it, right, would be, well, it'd start at the bottom, or it'd start, some height from the ground, right, and then it would go up, and then down. It'd be doing something like this, right? Because we'd be getting on at the bottom, and then it would be going up and then down, and there's our D value for our midline, and we have our amplitude and everything else, right? So I got to figure out how to like start the graph off that way. Well, I'm starting at a peak, right? So just, kind of like the last question, where I think cosine is going to be the one to go with here, because sine, if I was starting with sine, then I'd have to think about how far do I have to stretch this graph, or how much shift this graph over to get to that point. And I don't really know, right? So I'm going to start from a peak. So I'm going to use cosine. So let's write out y is equal to, and then our a value was 61, the radius of the circle, really. And then cosine, and then our b value was pi over 15. And then x, I don't know c, so I'm just going to leave that for a second. And then our d value was 74. So plus 74. Okay, so let's look at this a little bit closer. If we just used our typical sine graph or cosine graph, it's usually starting from here and coming down, right? Well, we're doing the exact opposite. We're starting from the bottom and then going up, right? And going that way. So all that we really need to do here is just this. We just need to like flip this thing over the x-axis. So there. Now I don't even have a shift. I don't even have to worry about shifting this thing at all. We could, right? It'd be fine. Yeah, we'll just, so that'd be kind of it. We just wouldn't even have to write anything there at all. But the other thing we could have done, if we knew what time we got to our max, then we could have shifted this thing from there to there and kept it positive, right? But this is good enough, and we don't really know when that happened anyway, so we'll leave it like this. So there's our equation. So yeah, I didn't really need that space. Okay, so just like that. Now it says, what are the what's the domain of our function, and where is it valid? So our domain will just be, x has to be, well, we got on here, didn't we? Okay, so, but people can jump on whenever, but we do have some point or some time that we started. So we'll say x has to be greater than or equal to times 0, where x is a member of the real numbers. And maybe I've been clear enough about that too. When we're doing this, right, our x value in these cases were time. And we knew that because of the 30 minutes that we had in there. Okay, so yeah, so we could have had t's in there as well. They'd be fine. All right, let's look at the next one here. So it says, how high above the ground would the passenger be after being on the ride for 1/3 of its duration? Okay, so we were told that the duration there, well, I guess duration for one cycle, I should say, right? Like one time around, would be, well, it was 30 minutes was the period. So then 1/3 of that would just be 30 divided by 3. So we're talking 10 minutes, right? So after 10 minutes, how high would you be? Well, we have an equation for that now, right? So now we can just plug that in. That would be y is equal to, y or h, I guess I could have been saying, is equal to negative 61 times cosine pi over 15. And then instead of an x, I'm going to put in the time, right? That's the point of a function. So 10. And then plus 74. So we get y is equal to 104.5 meters. Would be your height at that point, okay? So now the next part says, at what times would the rider be 100 meters above the ground? Okay, so let's kind of think about this a little bit more clearly. Actually, you know what? I'm going to graph this. Okay, so there is the equation that we made for this situation, right? For our Ferris wheel. So we're getting on at the bottom, right? So this all kind of makes sense. We get on at 13 feet. Sorry, I mean meters. And we want to know, so again, that's the max height, which makes sense as well. At what times will we be at a certain height? So our height is our y-axis, right? So at what times, they're saying like, what will the x value be when the y value is at, I think it was 100 meters it said, right? So 100 meters. So what we're going to have to do here is we're going to have to graph one more line. So I'm going to graph y is equal to 100. So now you can see, yeah, that straight line, right? So now if I figure out where these things cross, so there you go, there's one of them, right? This is going to be when the time is at 9.6 minutes, we're going to be at 100 meters. But it's also going to happen here. When x is 20.4 minutes, we're going to be at 100 meters. But then it would happen again at 40 minutes or whatever, if you're rounding up there. And it would keep on with that pattern all the way around, right? But this is the idea. So we can just stay right from the graph at 9.6 minutes. Okay, so the times would be at 9.6 minutes. And what did I say? 20.4 minutes. All right, next one. So it says the depth d meters of water in a harbor t hours after midnight can be approximated by the function d of t is equal to 12 plus 5 cos of 0.5 t, where t is greater than or equal to 0 and less than or equal to 24. Determine the maximum and minimum depths of water in the harbor. So I'm just going to graph this and we'll kind of just play around with this one because it's definitely just a graphing question. So y1, so I'm going to write this out instead of 12 plus 5 cos 0.5 t. I'm going to write the other way around just because I can. So I'm going to write this as 5. Oh, it doesn't like that. Let's go back. I'm used to Desmos. So 5, and I have to type in, or put in cos, and then 0.5, and then x, and then bracket, and then plus 12. All right, I should probably make this bigger. All right, so if we're looking at this, then I'll graph it quick, but we'll kind of see as we graph it. It's not a great window for what we're looking at, is it? We kind of got like a bit of the bottom. I need to see more up here, don't I? More up to the top. So let's change our window settings. So what's a good place to start? Well, I know that my D value here, right, is being shifted up to 12. So I got to be able to go up at least to 12, right? That will get me to the middle. So I don't know. Let's go with like 40 even, so we can see quite high. And then it would be nice to see, like I can tell here, I'm only seeing to the bottom of this one. Let's go a little farther to the right as well. So I'm going to go into my window. So my X min and X max, they're probably fine. I don't really need them that small, but that's okay. So our max, let's make that like 20. It was almost good, but not quite. But then our Y max definitely needs to change. So what did I say, like 40? Just to make sure we can see it. All right, let's try that one. So this is looking a bit better, right? We're getting this idea with the tides going up and down. Okay, perfect. So now determine the maximum and minimum depths of water in the harbor. Okay, so maximum, well, where are we going to find that? So let's, on this one, that's going to be under your calculate, right? To find a maximum. So go second, calculate. And yeah, number 4. And then it could be really either one, right? Because it's just like any of these maximums, because it'll be the same for every one. So I'll do this one over here just so it's kind of out of the way and got a bit more going on. So first off, it wants left bound. So I'm just going to go like just to the left of where I think the maximum is. And then just to the right. So enter. And then take a guess. So it's going to tell me that the maximum is at 12.6. Okay. Oh, no, sorry, that's max value. Maximum is going to be at 17. Okay. So, and actually, that was kind of silly. We didn't really need to do that, did we? So, the maximum there is going to be at 17, but we could have figured that out on our own too, couldn't we? Because this graph goes like, you know, up and down, right? So there's our D value, right? Our midline. And we know that that's at 12, right? So from there to there, so this was 12 from the bottom to the top, right? We know that because that's that midline value there, or D value, right? And then we can also see from the graph that our amplitude is 5. So it'd be really just this 12 plus 5. So I know that the maximum value here is going to be at 17. Right? So just 12 plus 5 is 17. Okay, so where would your minimum value be just using the same process, right? So we know it's going to be 12 to there. Well, the minimum is going to be down to here. So that's just going to be 12. So here the minimum is going to be 12 minus 5. So the minimum is 7, right? So 7 meters. Yep, meters. Here, this was the max. Okay. Determine the period of the function. Okay, so the period of the function is going to be related to our b value there, right? So our value of 0.5. So b was equal to 0.5. So then we know that p is equal to 2 pi over period, or over b. So here, let's do this again. So this would be 2 pi over, and then for my b value, instead of writing it as 0.5, I'm going to write this as a half. It'll just work out nicer. So this would be the same as a half. Dividing by a fraction like that, it's the same as multiplying by the reciprocal, flipping it around, right? That'd be the same thing as 4 pi. So our b value is 4 pi. Or sorry, I mean, our period would be 4 pi. And remember what our units are here, right? We're doing hours for our time. So this would really be like 4 pi hours. All right, so the next one says write a suitable window, which can be used to display the graph. So I already did that. I kind of did this in a little bit in reverse, but that's fine. So let's look here and see what I chose for my window there, my window settings. So it's looking for this, right? So X min, X max, and my scale. So there's an infinite number of answers here that would be fine. So I just write X and then my little bracket there. So that would be whatever I had for my window. So that was, whoop, wrong one. Negative 10, 20. So negative 10, 20. And then the 1 is just my scale. That just means what it's going up by. I don't really care that much about that. If you're using a TI Inspire, you can set that to auto and it just kind of chooses the most appropriate. But we don't really care how many ticks it goes up by. Okay, and then our y. So our y would be negative 10, 41. Okay, and that's just a way of letting your instructor know that you're actually looking at it, right? Okay, so what is the depth of water to the nearest tenth of a meter at 2 a.m.? Okay, so it's asking for what is y, right? Where my d value at 2, right? And we're starting at 0, like so midnight, right, would be our time 0. So 2 a.m. really would just be 2, right? The time of 2 that we can put in there. So this would be what is d of 2 of 5 times cos 0.5. And then, even though it doesn't have brackets, this part is all in brackets, right? 0.5 times, like square brackets, times 2, and then plus 12. All right, so that would be equal to 14.7. And then, what was that in meters? All right, so it says a ship requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest minute must it leave to prevent grounding? Okay, so we want to know what the time should be at 8.5 minutes. So really we want to make a line at y is equal to 8.5, right? So let's actually go back to our graph here and we'll just do it again. So we'll go y is equal to, and we're going to type in 8.5. and graph it. Okay, so in order to avoid grounding, right? So at like when it's leaving here, right? Okay, so if we were thinking about this, so if the ship is here at midnight, right? Then what it doesn't want to do is it doesn't want to, start leaving during this time, and then as the water's going down, it would ground, right? So it'd actually be better if it waited until the tides start going back up again for it to leave, right? So it'd like to leave actually on that second point right there. So let's go calculate, and we're going to find the intersection for that point. Oop, wrong one. Okay, so we're going to go first curve is still going to be the blue one, but I just want to make sure that we're in kind of in the right spot there. It says yes, take a guess. So the intersection there is going to be at 7.87. Okay, so 7.87, which would be, 7.9 hours is when it should wait to leave, right? Okay, what is the next time to the nearest minute that the ship can return to the harbor? So again, if we're looking at our graph here, right? So if it leaves, right? So it's left the harbor, time's going by. It doesn't want to come back like any time over here, right? It actually wants to come back into the next phase there, right? So let's go back over here again, and we'll increase our window setting there. So we'll go look a little bit farther to the right. So we'll change our X max to 30. Okay, so then we're just going to do it again, but now we're going to want to wait until this point over here, if you can see the tip of my pen there. Okay, so we'll go trace, not trace, we'll go second calculate, intersection, so 5, and now we'll move all the way over here. Okay, so enter, enter, take a guess. So that's going to be at 20.4. So that's going to be after 20.4 hours on the 24-hour clock. All right, last one. The tides in a particular bay can be modeled with an equation of the form D is equal to A cos B times T plus C, where T represents the number of hours since high tide, and D represents the depth of water in the bay. The maximum depth of water is 36 feet. The minimum depth is 22 feet, and high tide hits every 12 hours. Sketch a graph of the scenario for 2 full periods. Label the points on the curve that represent the high and low tides. Okay, so if we're going to sketch this thing, okay, I'm going to make it something like this, because actually I know that my high and my low are going to be above 0, so I'm going to leave space up here. So up and down, this is going to be my depth. So my D, or my depth up and down. This is going to be my T. All right, so if we're going to sketch this thing, we got to kind of get our bearings here first. We're using a cos graph, it's telling us, right? And a cos graph, if you remember, starts up top and then comes down, right? So that's exactly what we're going to have going on now, right? And so we're going to be starting at the peak. And it even said that. It says the maximum, yada, yada. Oh yeah, D represents, what did it say? Where T represents the number of hours since high tide, right? So this is going to be high tide is where we're starting. And then this thing comes down, all the way to the bottom, and then up again, and then down, and then up again. And that's probably good enough for now. So to begin with, that very first point would have happened at 0, comma, and then 36 feet. And then our low point would have happened at, well, you know what? Before we do our low point, let's figure out our other high point. Because they actually tell us, don't they? They say that this happens every 12 hours, right? It says that we have a high tide, right? A high tide every 12 hours. So I know this point is going to be 12, 12 comma 36. Okay, so that's going to help me out for, this value, right? Because now I can see that my x value here would be half of that, right? Halfway between it would be our low point. So that's going to be at 6, 22. And then we'll just keep filling this in. So then it's going to be 6 more after 12, right? So this is now, the next point would be 18. So that's going to be at 18, 22 for our low. And then another 6, so that's going to be at 24, 36. And there you go. That's our sketch. All right, so now we're just going to find the values of A, B, and C. And just be careful on this because our C is really our D in our equation. Y is equal to A. Here, I'll just write it out. There, just wrote it out a little quick. That's really our D value, isn't it, right? That's outside of the function. That's outside of f of x there. So, yeah, that's going to be our midline, okay? So let's find the A and B. Those ones are labeled correctly so far because that would be our typical B value there. So we'll do A first. So A is going to be, well, just to remind us what we're looking for here. Your A value is the distance from here to here. Okay, so this one is just going to be your max minus your min divided by 2, right? So 36 minus 22, and then cut that in half, and that's going to give you the height there. So A is equal to 36 minus 22 over 2. So 7. All right, one down. So next one here. So now we'll find our B value. So for our B value, we're going to need to know what the period is, right? Because B, well, here, you know what? Let's find C while we're on that same. Sorry for jumping around. Let's find our C value, which is like our D value typically. So C will be, well, just the average between 36 and 22, right? That's for that midline. So this would be your max plus your min divided by 2. So C would be 36 plus 22 divided by 2. So 29. All right, 2 down. So last one is just to figure out our B value there. So remember B is equal to 2 pi over the period. Okay, so that's going to be B is equal to, and then 2 pi, and then they told us the period, didn't they? They told us that it was, it's high tide every 12 hours. So that would be from high tide to high tide. That would be one cycle through. So every 12 hours is my period here. So this is going to be 2 over 12, which would be the same thing as pi over 6. So just for good measure, let's type this in, or actually write out the equation for this, right? So this would be D is equal to 7 cos, and then our B value of pi over 6 x, and then our C value was plus 29. All right, last one. Tanker boats cannot be in the bay when the depth of the water is less or equal to 25 feet. Set up an inequality and solve it graphically to determine all points in time t on the interval between 0 and 24 when tankers cannot be in the bay. Round to the nearest tenth of an hour. Okay, what are we talking about here? So this is really taking this equation, right? So we want to say, okay, where are all the times, like what are the allowed times when we're less than 25 feet, right? Because that's where we're setting it up for, where they cannot be in the bay. So we want to have everything less than 25 feet. Okay, so let's set this up. I'm actually just going to write this equation out again. So this would be D is equal to 7 cos pi over 6. And then I said x above, but technically I guess it should have been a t, right? Because this is our time. And then plus 29. Okay. And now, really, I want to know where is this, right? This like d value, because all of that together would be like my depth. this needs to be less than or equal to 25, right? So we're going to solve for like what are the values for t that would make this true. Okay, so there's actually going to be a whole bunch of numbers that are going to make that true. So we're going to write our answer as an interval in interval notation. Okay, so here it shouldn't be d is equal to all this. It would just be this is less than or equal to 25. Okay, so what we're going to do here is I'm going to graph this side of the equation as my y1 and this side of the equation as my y2. All right, so I'm going to do it on Desmos again because it's nicer. Okay, so this was 7 cos pi over 6, and then I'm going to put x in here, not a t, and then it was plus 29, right? Let me double check on that. Yep. Okay, so that was my one equation, and now my other equation will be just 25, right? So I'm just going to draw the line 25. So on Desmos, you can't just write 25. I have to go y is equal to 25 if I'm just putting in a constant term. So yeah, they're saying like what are the places where this is true? Well, it's going to be true from here to here, right? That's where the red line is below the green line, below 25, and from here to here. So we just need to write that out in the proper notation. So I'm just going to write it right on the screen here so you guys can we can kind of go piece by piece. And the other part I'm going to do is I'm going to click on these dots so that I can see what the points actually are. All right. Okay, so the y values would obviously all be at 25 because that's what I'm referring to, or how I want to be less than or equal to that. So if we were writing this in interval notation, then I'm just going to start at this point and end at this point for my first one. And it's less than or equal to, so I'm going to use a square bracket. So I'm going to say it goes from 4 point, and I think I'm supposed to round to the nearest 10th. I better check. We are supposed to round to the nearest 10th of an hour, yeah, okay. Okay, so 4.2, comma, and then I'm just going to go to this one, so that would be 7.8. 7.8. Okay, so that handled the first one. And then technically you'll see things where it will say like and, you know, but technically we should be using like a union symbol. So it's this unioned with now this part. So then we're just picking up where we left off. So now it's from 16.2, comma, and then 19.8. And it included all of those points. And now our interval was only for 0 to 24 hours, right? So 24 would be, you know, you guys can, it's off the screen a little bit, but it's not going to include any more below this, right? So that's good enough. That's going to be our answers in interval notation for this one. Okay, and I just wrote it on this sheet as well, so.